All right, welcome. The purpose of this video is to walk you through Key Assessment Unit 6, Balanced Forces and Constant Velocity. I'm going to be showing you kind of where you could have found some of the information and helping clarify some of the questions. It is required that you watch this video for any questions on which you lost marks. So feel free to skip around if you got full marks in a question, but you do need to check in for any of the places in which you lost marks. The first mark was right here, replacing your name, agreeing to the honor policy. We did tell you during the test directions that this was now a mark on the test, so thank you. The vast majority of you did that. If you lost this mark, please pay attention to that next time. All right, so I'm going to work through question by question. Let's get started with part 1, Forces in Motion, part 1A. 1A asks you to draw a free body diagram. Well, where did we see free body diagrams in class? We saw it on Unit 6, Day 6. We talked about free body diagrams. We talked about how if you have balanced forces, that indicates constant velocity. And you actually had a practice in your homework that was exactly about a skydiver. So you've actually already practiced with a skydiver. Here is the question in your homework. Here is the question on the test. Same exact idea. And so we were just looking for a free body diagram with two balanced forces here labeled appropriately. So this force would be air resistance, and you should write it out completely. And this force would be gravity. All right, describe how the forces caused Miss Miller to have a constant velocity. That's what we talked about here on this day. What causes constant motion? Well, the thing that causes constant motion is balanced forces. So this question asked you to describe the forces. One thing I saw there was people trying to talk about other things not related to forces. Make sure you notice the question specifically asked about forces. So what we're looking for there is that you mention that the forces are balanced. All right, question 1. Let's get into part 2, data collection. You hopefully saw that part 2 matched up really closely with what we did in the car lab. So take a look at our presentation from car lab part 2. This is car lab part 2. Notice that we actually did the same activity in class. So in class, I asked you to match a precision mistakes and add it to the chat. I think with a few sections, we did this via Zoom Annotate. So this was an activity that we did in class. This is slide 16. And you were, of course, noticing that the precision of your data should match the precision of your measurement uncertainty. So it's not that one data point needs to match another data point. It's that all of your data points need to match your measurement uncertainty. So making the corrections, that's exactly like what we did in class, explaining why. The first point there was just mentioning that all of the data needs to match a measurement uncertainty. The second part there was a little bit of an inference, really pushing towards that 7 level. Several people got this point. The second point in this one was trying to explain why that needs to be true. It's a little bit of an inference. It pushes on your understanding of what measurement uncertainty is. We know if this is how accurate we can, or how precise, I should say, how precise our measurement can be, well, then none of our data could possibly be more precise than that, because we've already established this is how uncertain we are, plus or minus 3 meters. And so all of our data falls under that same measurement uncertainty. We can't be any more precise than the measurement uncertainty. So some sort of attempt at that explanation got you the second mark there. All right, question 2. Question 3, control variables. So people generally did a good job mentioning a control variable, stating a control variable. The biggest thing here was the explanation. Notice under control variables, we mentioned that the variables you hold constant so that you can see if there's a relationship between IV and DV. That's what we're trying to do in all of these cases, right? We're trying to explain how does one thing affect another. In this case, we were trying to explain how does the time, our independent variable, affect the displacement. So the idea of control variables was we need to control everything else that could affect displacement that's not time. So if I see a result, if I see an effect, I can say, okay, there's evidence that the effect I'm seeing is coming from time and not coming from something else. So things like same weight, same parachute, even same weather, those were all accepted here. And then for the explanation, I was really looking for you to say something about my control variable would affect the dependent variable. And so I would not be able to conclude that the IV was the thing causing the effect I saw. So some sort of general explanation of what a control variable is and the importance of controlling it in terms of dependent and independent variables. And then the second mark here was explaining your particular example. Why did your example need to be controlled? So for example, if you chose weight, why is it so important to keep weight consistent? What would weight affect that would then affect the experiment? The thing that I saw here, the biggest thing that I saw here was people being really vague, saying things like, it would have an effect, it could change the data, it could make the data less reliable. And I would really push you here to think about why. If you're saying that it could have an effect, well, the next thing you should say is, what is the effect? If you're saying that there's some sort of potential change in the data, you should explain what is that change. So lack of specifics lost a lot of people the second mark here. Many people were good at identifying. If you lost marks here, one thing you can improve on is being more specific, not just saying there's an effect, and really that should be effect, not affect, excuse me. Not just saying there's an effect, not just saying there's a change, or just vaguely saying reliability, but being really, really specific. All right. Moving on, so that was question 3. There we go. Moving on to question 4. Question 4 was all about uncertainty. There were 2 days that we talked about uncertainty. We talked about it in Car Lab Part 1. We also talked about it again in Car Lab Part 2. That should really check in for you. If there's 2 times we talk about something, it's probably pretty important. So the first question, why did we need to include uncertainty? Well, that's because every single measurement, in every lab has uncertainty. Every single measurement is some sort of estimate. So you always include uncertainty, because always, whether you're using a digital tool, a physical tool, whatever kind of tool you're using, all measurements we make in lab are actually estimates. How could the scientists have determined the uncertainty? Well, we talked about 2 major sources of uncertainty. One is the instrument, something about the instrument. So in this case, because it was a ruler, something about the tick marks and the fact that we need to estimate between tick marks. We also discussed the impact of the human making the observation. So like in the example we saw with the car, Sometimes there's a little blurry, there's a little bit of a shadow, and so that would affect our results. So in this case, we were looking for you to say we need to include uncertainty because every experiment has uncertainty, every measurement has uncertainty. And then in the second part, we were really looking for you to mention these two big themes we kept coming back to, that the instrument itself has uncertainty and the human interpretation adds some uncertainty. So when you combine those two, you get your uncertainty value. This is particularly true in a situation like this in physics, where we have a video and there's motion and there's the potential for it to be blurry, for it to be hard to estimate. So that human interpretation piece really comes in. Lots of people earn partial credit here, and we tried to be flexible. If someone did some explaining in part A, you might have gotten credit for that. But you needed to mention all of those points in order to achieve all 3 marks for question 4. All right, question 5, graphing. Well, as you know, you did graphing in Car Lab Part 2. You practiced graphing, and it looked exactly like the graph that you made. We also even gave you the checklist of what we were looking for, so many people did really well with graphing. Honestly, the biggest thing I saw in graphing was people, instead of saying IV versus DV, time versus displacement, several people wrote displacement versus time. The title, just like it told us here, is time versus displacement, time versus displacement. And you saw on our slides, we had a couple slides where we actually showed you example graphs. Here's our example graph and time versus average displacement. Some people are very, very specific. Time since the parachute was opened versus average displacement fallen, which is great too. So this one was generally well done. And again, you practice this in Car Lab Part 2. All right, question 6. Question 6 really came out of Car Lab Part 3. So you'll notice for Car Lab Part 3, we spent this entire day walking through how to set up this equation. We worked through together how to set up the equation, how to find the slope, how to find the y-intercept, and then how to put the equation together and find its units. And so notice, if we're walking you through something step by step, that means it's probably really important. We're probably going to assess you on it. So if you were in class as we were doing this and you were not sure what went in each box, well, that was your job to stop us and make sure that you knew exactly what we were doing so that you would be able to reproduce it on an assessment, because you see the same sort of idea came up. This again was Car Lab Part 3, and you are following along on your Car Lab Part 3. In terms of the explanation, same deal. So for all of question 6, we walked you through this on the day that we talked about Car Lab Part 3. So we described the slope. The slope, of course, relates to velocity. It tells me in 1 second I've traveled however far the slope is. So in this case, 15.8 meters, you would put your slope. And then we also walked you through interpreting the y-intercept. The y-intercept is a little tricky in this case because it was a little bit different from the car. The y-intercept is telling us time since the parachute had opened. So some people were a little confused about that. We showed you the video of the parachute. This is a plane, as you can obviously tell with my wonderful art skills. So we saw the video at the beginning of the test where the person jumped out of the plane, they fell for a while, and then after a while, this person adds the parachute. So here they are with a parachute, and then they keep falling. And at some point, as they keep falling, we start collecting data. Our independent variable was time since the parachute was opened. So we start collecting data at some point here when the parachute has already been opened for a little bit. So the y-intercept in this case was the displacement, the person's displacement, how far they had gone since the parachute had opened, the person's displacement at time equals 0, for our experiment. So the person's displacement at time equals 0 seconds. It was not the starting position. It's not where the person started. The person started way back here in the plane. It's the time since the parachute was open, the person's displacement since the parachute was opened at time equals 0. Some people wanted to write about how this situation didn't make sense because they were thinking about the car lab and this question here. We didn't take off for that, but in this case, the situation did make sense. It did make sense to have a y-intercept value because that's where we started recording data. All right, question 6. Question 7, problem solving. All right, so as you know, you practiced problem solving the day that we did problem solving with S equals VT. You practiced this on your own in base camps. The first question was a pretty straightforward question, like one of these initial ones that we did. You were looking for time, just like this very first example we walked through together. The second one was a little bit more complicated because there was an initial starting displacement. This third one was matched up with kind of our complex situation. Notice, the day that we did S equals VT problem solving, we told you that those complex situations were fair game for the test. I got a few last-minute emails the day before the test asking me what fair game for the test means. If you ever see something on a slide, you can always ask during class and should ask during class. But some of you were asking, oh, what does this fair game for the test mean? Well, fair game for the test means it's fair for us to put it on the test. We're telling you that it could show up on the test. So, unsurprisingly, a complex problem-solving situation did show up on the test. All right, before we walk through how to do each of these problems and how to set these up, I just want to point out a couple other resources that you have. All of these problem types we covered in our review. So we had 2 days of review for this unit. You'll notice within the options, we covered measurement uncertainty, we covered data collection and graphing, we covered analysis, that's setting up those equations, we covered problem solving and force body diagrams. You also have access to our keys. Now, no one is recommending or suggesting or in any way implying that you should just open up the keys and try to memorize the information. That's not learning. That's not how science works. But I do want to point out that this is a really helpful resource for you. If you're feeling unsure about measurement uncertainty or you don't know that you could fully explain measurement uncertainty, using the review option key can help you check yourself. And then if you encounter something in the key that's different from what you thought after you tried the problem on your own, that's a good indication that you can come to office hours, you can come chat with us, you can come tag us to make sure you get any questions answered before the assessment. So I just want to point out that these resources exist. These resources are here for you to use. Make sure you're taking advantage of everything that we're offering you. All right, thank you so much.